All right, so last time we talked about KSP, and we said KSP is the solubility product constant. But when we're talking about solubility, we don't always use KSP. Another commonly used term is molar solubility. And so molar solubility, as the name implies, is the solubility in moles of solid dissolved per liter of solution, right? So moles of solid dissolved over liters of solution. And so we have two different units that are describing essentially the same thing. And so the good news is we can interconvert between the two. So let's take a look at going from KSP, which is in this case our given, to molar solubility. So we're going to take a look at lead chloride, and it's going to dissolve into one lead, 2 plus, and then 2 chloride minuses. And so we're told the KSP value here is 1.17 times 10 to the negative 5, and we want to solve for the molar solubility. And so naturally, what we want to start off with is our Rice table, because molar solubility is going to be how much of your stuff is dissolved at equilibrium. Remember that this lead is a solid, and so we can just ignore it in our Rice table. Initially, we'll say that we have 0 concentration of either one of these, and then we're going to dissolve some stuff. So this is going to increase by plus x, and then this is going to increase by plus 2x, right? This coefficient is 2, so plus 2x. And so then at equilibrium, we're at x and 2x. And then we can write our KSP. So in this case, our KSP is going to be equal to the concentration of lead 2 plus times the concentration of chloride squared. And so now we can plug these numbers into here, x for the lead, and then 2x for the chloride. So then we have x times 2x squared, and then we know it's also equal to 1.17 times 10 to the negative 5. Solve mathematically here. So x still here, 2x squared goes to 4x squared. And then x times 4x squared is 4x cubed. And then we're going to divide by 4 and then take the cube root or raise it up to the 1/3 power to solve for our x, 1.43 times 10 to the negative 3 molar. And now we need to think about what is our molar solubility and how does it relate to our x? Well, so let's talk about this over here. So we can think about it for every 1 lead chloride that's dissolved, you get 1 lead, 1 Pb2 plus, and 2 chloride minuses. And so thus the molar solubility of lead chloride will be equal to the concentration of lead in the solution. And that's our x. And so if you set it up kind of the way I did here, it's almost always going to be equal to x. But you just kind of want to be careful and think about what you're talking about. And remember, molar solubility is the amount of moles that got dissolved, the amount of moles of the solid, right? So in this case, it'll be equal to the amount of lead at equilibrium, but only half of the chlorides, or in this case, equal to x. And so in this case, this is our molar solubility. And so here's just a table with some different KSPs of different compounds, right? So a lot of these compounds you were told were insoluble in water, and you can see overall, generally speaking, they are. Most of these K values are quite small. Let's just do one more example. So find molar solubility of iron sulfide. And you're given that the KSP here is 3.72 times 10 to the negative 19. Right, pulled that right from the table, right from here. And so we can draw up our rice table. So we know that iron sulfide will dissolve into Fe2 plus S2 minus. We know iron sulfide's a solid, so we can ignore that side. Say that the initial concentration here is 0, and then this will be X plus X. This one will also be plus X because both coefficients are 1. So this ends up being X and X. And so then KSP is equal to the concentration of iron times the concentration of sulfide. In this case, they're both just equal to X. And then we know it's also equal to this 3.39 or 3.72 times 10 to the negative 19. And so what we have to do to solve for X is just take the square root of both sides. And in this case, our X is equal to 6.099 times 10 to the negative 10 molar, right? And in this case, right, for every one iron sulfide that dissolved, we're only going to get one iron or one sulfide. So it's going to be equal to our X values. And so again, this is our molar solubility. So if you set it up like this, your molar solubility will always be equal to X.